On the morning of 11 November 1967, a fire was discovered aboard the British aircraft carrier HMS Victorious, then undergoing a refit at Portsmouth Dockyard. The blaze began in the senior rate's mess deck. The ship's company, assisted by dockyard and city firefighters, brought it under control. But the incident was not trivial. One sailor lost his life, and 2 others were taken to hospital. Repair work began almost immediately. The fire had not destroyed the carrier. It had not torn open her hull, ruined her flight deck, or rendered her machinery beyond recovery. But it had struck at the worst possible moment. Victorious was already more than 20 years old. She was scheduled to leave service in 1969. Completing her refit and repairing the fire damage would cost additional money, while keeping her operational would preserve a ship the government had already decided it would soon no longer need. Within weeks, the decision was made. HMS Victorious would not return to sea. The fire did not physically kill the ship. It destroyed the remaining economic argument for saving her. That would have been a quiet ending for almost any aging warship. But Victorious was not an ordinary survivor. She had already been built twice, first as an armored carrier for the Second World War, and then almost completely reconstructed as a weapon for the jet age. Her second construction took nearly 8 years. It absorbed almost 20 million pounds. It replaced much of the ship above the hangar deck, introduced new boilers and machinery, and brought together some of the most important innovations in the history of naval aviation. The result was neither a simple triumph nor a simple failure. HMS Victorious proved that an old hull could be transformed into an advanced jet carrier. She also demonstrated the cost, delay, and compromise involved when the requirements of the future are forced into the dimensions of the past. This is the story of the carrier Britain built twice, and why the second construction became far more difficult than the first. When the Second World War ended in 1945, the aircraft carrier had established itself as the dominant capital ship at sea. But the carriers that had won the war had been designed around piston-engine aircraft. Most used an axial flight deck, a straight runway running along the center line of the ship. Aircraft landed from the stern. Farther forward, other aircraft waited to be launched, serviced, refueled, or rearmed. The 2 operations occupied the same narrow strip of deck. To prevent a landing aircraft from crashing into the machines parked ahead, carriers used arresting wires and emergency barriers. If the aircraft's hook caught a wire, it stopped normally. If it missed, the barrier offered a final chance to prevent it from reaching the forward deck park. This arrangement was already dangerous. The arrival of naval jet aircraft made it increasingly unsatisfactory. Jets were generally heavier and approached the carrier at higher speeds. Early jet engines could also respond slowly to sudden throttle changes. A pilot who recognized a poor approach late in the landing had less time and less margin to recover. If the aircraft missed the arresting wires, it could strike the barrier with far greater energy than the piston fighters for which the system had originally been developed. Even when the barrier prevented a larger disaster, the damaged aircraft could block the landing area. Other aircraft still in the air might then be forced to wait while their fuel continued to fall. Launching jets created a second problem. Existing hydraulic catapults had been designed for lighter aircraft. As naval aircraft grew heavier, the amount of energy required to accelerate them safely from a short deck increased dramatically. The carrier had not become obsolete, but its basic geometry and machinery had to change. Extending the straight deck would not solve the central problem. Landing aircraft, launching aircraft, and parked aircraft would still be competing for the same space. The Royal Navy, therefore, began looking for a way to separate them. One of the most important ideas came from Royal Navy aviator Dennis Campbell. Instead of placing the landing path directly along the center line, Campbell proposed turning it several degrees toward the port side of the ship. The change appeared simple on paper. In practice, it transformed carrier aviation. With an angled landing area, an aircraft that missed the arresting wires was no longer aimed directly at a barrier and a deck full of parked machines. The pilot could apply power, continue along the angled path, and fly back into the air. The maneuver became known as a bolter. The angled deck also made it possible to recover aircraft while other machines remained parked or prepared for launch farther forward. Landing and launching operations were no longer completely dependent on the same straight runway. The British tested the principle before carriers were rebuilt with permanent angled decks. The United States rapidly joined the development process, and USS Antietam emerged in late 1952 as the first American carrier fitted with an experimental structural angled deck. The solution to the launch problem came from another British officer, Commander Colin C. Mitchell. Mitchell developed the slotted cylinder steam catapult. Instead of relying on the limited energy available from earlier hydraulic systems, the new catapult used high-pressure steam to drive a piston along a cylinder beneath the flight deck. The piston transferred its force to the aircraft through the catapult shuttle, producing sustained acceleration over the length of the launch stroke. A prototype was installed aboard HMS Perseus. In 1952, the ship visited the United States and demonstrated the system to American naval experts. The technology offered the power required to launch increasingly heavy jet aircraft. The United States Navy adopted it, and steam catapults became a defining feature of large Western aircraft carriers for decades. The third major innovation addressed the landing approach itself. Traditional landing signal officers, known in the Royal Navy as batsmen, stood near the landing area and used paddles to guide pilots. With faster aircraft, pilots needed a more immediate and continuous indication of whether they were above or below the correct glide path. Commander H.C.N. Goodhart helped develop the mirror landing site. The system projected a light into a stabilized mirror. From the cockpit, the pilot saw the reflected light in relation to a fixed row of datum lights. Its position showed whether the aircraft was too high, too low, or following the correct approach. The mirror did not make landing automatic, nor did it remove the landing signal officer from the process. The LSO continued to monitor approaching aircraft and respond to emergencies. But the pilot now possessed a continuously updated visual reference rather than relying primarily on paddle signals. Angled decks, steam catapults, and optical landing aids became the foundation of conventional jet carrier operations. They were not all first proven aboard HMS Victorious. The steam catapult was tested on Perseus. The mirror landing system underwent trials aboard ships including HMS Illustrious. Angled deck concepts were tested in Britain and developed rapidly in the United States. The importance of Victorious was different. She would become one of the first ships in which these separate developments were integrated through an extraordinarily deep reconstruction. HMS Victorious had been laid down in May 1937. She was launched on 14 September 1939, less than 2 weeks after Britain entered the Second World War, and commissioned in March 1941. She belonged to the Illustrious class, whose defining feature was an armored hangar and flight deck intended to protect the ship against bombs and shell fire. That protection proved its value during the war. Soon after commissioning, aircraft from Victorious joined the pursuit of the German battleship Bismarck. One of her Swordfish torpedo bombers scored a hit, although the damage was minor. It was a later attack from HMS Ark Royal that jammed Bismarck's steering gear and sealed the battleship's fate. Victorious went on to support Arctic convoys, operations in the Mediterranean, the Allied landings in North Africa, and attacks against the German battleship Tirpitz. In 1943, she temporarily served alongside the United States Navy in the Pacific, operating with USS Saratoga. Later, as part of the British Pacific Fleet, she survived kamikaze attacks that demonstrated the resilience of her armored design. But the armor that protected her during the war would complicate her post-war transformation. An armored carrier was not an empty shell. Its internal spaces were enclosed by heavy, rigid structures. Compartments, lifts, machinery, magazines, workshops, and aviation fuel systems had all been arranged for aircraft of the late 1930s. Jet aircraft required more space, more fuel, more electrical power, stronger deck equipment, and more complex maintenance facilities. Modernizing Victorious, therefore, meant far more than adding a few new devices to the flight deck. The ship would have to be opened up and reconstructed around requirements that had barely existed when her keel was laid. In 1950, HMS Victorious was taken into Portsmouth Dockyard for modernization. The decision was made in a Britain still carrying the financial consequences of the Second World War. The country was trying to maintain a global naval role while controlling military expenditure and rebuilding its civilian economy. Modernizing an existing carrier appeared to offer a way of preserving fleet strength without starting an entirely new ship. But the original plan did not include everything that Victorious would eventually receive. Carrier technology was changing so quickly that requirements evolved while the ship was already being dismantled. The angled flight deck, for example, was among the major improvements added after the initial decision to modernize her. Each new requirement affected other parts of the design. A permanent angled deck was not merely a painted line, it required new supporting structures extending beyond the original hull. Larger and heavier aircraft demanded stronger arresting gear, more powerful catapults, additional aviation fuel, revised workshops, and changes to aircraft lifts and deck handling arrangements. The ship's hangar required major alteration. The island was replaced. New communication systems, electrical equipment, magazines, ventilation, and fire control arrangements had to be fitted into a hull designed before wartime radar had matured. The immense Type 984 radar and its comprehensive display system added another layer of complexity. Type 984 was a three-dimensional radar capable of providing range, bearing, and height information. Combined with its display and control system, it allowed the carrier to coordinate fighter interceptions across a wide area. It was among the most advanced shipborne aircraft direction systems of its period. But advanced electronics required space, power, cooling, operators, maintenance facilities, and extensive cabling. Installing them aboard an existing armored ship meant routing modern systems through a structure never designed to accept them. The propulsion plant was also addressed far more extensively than some accounts suggest. Victorious did not return to service using untouched boilers from the 1930s. New boilers were included in the reconstruction. The project's difficulty came not from refusing to replace them, but from the enormous accumulation of changes across the entire ship. The carrier was stripped down from the hangar deck upward. Her hangar height was increased. Her hull was lengthened and widened. She received new boilers, a new flight deck, new catapults, new landing aids, new radar, and a substantially rebuilt island and internal arrangement. At some point, the distinction between modernization and reconstruction became largely semantic. This was no longer an old carrier receiving an update. It was a new aviation system being constructed inside the surviving structure of a wartime ship. The reconstruction was originally expected to finish much sooner than it did. Instead, HMS Victorious remained in dockyard hands for almost 8 years. Part of the delay came from the expanding technical requirements. Part came from labor shortages and the stop-start pattern of post-war defense spending. Work slowed, priorities changed, and sections already planned or completed had to be reconsidered as the Navy attempted to keep the design relevant. The world outside Portsmouth did not stop moving. While Victorious was being rebuilt, the steam catapult demonstrated aboard Perseus was adopted elsewhere. Mirror landing sites entered service. Angled flight decks appeared on British and American carriers. The United States, with a far larger shipbuilding program, incorporated the new ideas into both converted wartime ships and new carriers. USS Forrestal, commissioned in 1955, represented a different approach, a large carrier designed for jet aviation from the beginning rather than reconstructed inside the boundaries of an armored wartime hull. By the time Victorious returned, the inventions included in her reconstruction were no longer experimental curiosities. They were becoming the international standard. The cost of the project rose with its scope. A former Admiralty financial official later recalled that the original estimate had been about £5 million. The official figure given to Parliament after completion was nearly £20 million. Accounting definitions and later estimates sometimes produced other totals, but the central fact was clear. The modernization had cost several times more than initially expected. The overrun did not prove that rebuilding old ships was always irrational. Navies have successfully modernized warships throughout history. But Victorious illustrated a particular danger. When the scope of a modernization grows repeatedly, the Navy pays both for new technology and for the labor required to force that technology through existing armor, bulkheads, and machinery spaces. A new ship begins with empty space and a design organized around its intended systems. A reconstructed ship begins with boundaries. Every improvement must negotiate with steel that is already there. The reconstruction was completed in December 1957. HMS Victorious formally recommissioned on 14 January 1958. The ship that emerged bore little resemblance to the carrier launched in 1939. Her flight deck extended beyond the old hull lines. A new island rose on the starboard side. Above it sat the unmistakable face of the Type 984 radar, giving the carrier a silhouette that seemed to belong to another generation. Her new steam catapults could launch heavy naval jets. Her angled deck allowed aircraft to miss the arresting wires and return safely to the air without being directed into a barrier. Her optical landing system gave pilots a continuous glide path reference. Below deck, new boilers and rebuilt machinery supported a ship carrying far more electrical and aviation equipment than her original designers could have imagined. She was not as large as the new American supercarriers. Her armored origins and limited dimensions still constrained the number and type of aircraft she could operate. But in radar and fighter direction, she was exceptionally capable. During exercises with the United States Navy, her Type 984 radar and comprehensive display system demonstrated the ability to coordinate large numbers of interceptions. In one parliamentary account of a 1960 exercise, fighters directed from Victorious intercepted more than 90% of approximately 150 simulated attacks. The long reconstruction had produced a real frontline carrier. The question was no longer whether the technology worked. It was how effectively the complete system could operate under the pressures of deployment. In the summer of 1961, Iraq's claim to the newly independent state of Kuwait created the threat of an invasion. Britain launched Operation Vantage, rapidly deploying naval, air, and ground forces to deter Iraqi action. HMS Victorious, then serving in the Far East, was ordered toward the Persian Gulf. She arrived with Sea Vixen fighters, Scimitar strike aircraft, airborne early warning gannets, and the most sophisticated fighter direction equipment available to the Royal Navy. Her presence mattered. The carrier gave the British force aircraft that could operate without depending entirely on local airfields. Her radar and control teams contributed to an air defense network over Kuwait and the surrounding waters. Naval controllers successfully directed interceptions involving carrier aircraft and Royal Air Force hunters. The Type 984 system demonstrated the value of a carrier not merely as a floating runway, but as a command center for air operations. But Operation Vantage also exposed the difference between possessing advanced equipment and sustaining it under extreme conditions. The official naval history of the operation recorded serious problems with aircraft serviceability. Victorious had arrived after operating in monsoon conditions. Aircraft exposed in the deck park suffered corrosion. In the Gulf, sand and intense heat created further electrical, electronic, and mechanical defects. The Scimitar was powerful, but it was not an ideal interceptor. The carrier depended mainly on its Sea Vixens for that role. The climate also reduced the offensive load the Scimitars could carry. A carrier launching aircraft depends not only on its catapult, but on the combined speed of the ship and the natural wind across the flight deck. In the Gulf, high temperatures and weak winds reduced aircraft performance. Even with Victorious steaming at high speed, heavily loaded Scimitars sometimes required more wind than the weather provided. The aircraft could still be launched, but often with reduced fuel or weapons. the limitation was not caused by unreplaced pre-war boilers. Contemporary reports stated that the ship's main, flight deck, and auxiliary machinery generally continued to operate satisfactorily. The more serious weaknesses involved aircraft reliability, catapult performance under demanding conditions, cooling equipment, liquid oxygen production, and the ability of the ship and her crew to function in extreme heat. Air conditioning became an operational issue rather than a question of comfort. Compartments deep inside the ship became exhausting places to live and work. Equipment designed for more moderate conditions struggled as seawater and air temperatures rose. Reports warned that fatigue and heat could limit sustained operations even when the carrier's principal machinery remained functional. Operation Vantage therefore provided a more complicated verdict than either triumph or failure. Victorious delivered advanced radar, fighter direction, and mobile air power to a crisis far from Britain. Those capabilities contributed to a successful deterrent operation in which no Iraqi invasion occurred. At the same time, the deployment revealed the limits of operating complex jets from a reconstructed carrier in one of the world's harshest climates. The ship worked, but she did not work without compromise. After Kuwait, HMS Victorious continued to serve in the Mediterranean and Far East. She supported British operations during the confrontation between Indonesia and Malaysia and remained an important symbol of British maritime power. Yet the strategic world around her was changing faster than the ship itself. Naval aircraft continued to grow larger and heavier. The Blackburn Buccaneer could operate from Victorious, but each new generation placed greater demands on deck space, catapults, arresting gear, maintenance facilities, and fuel capacity. The Royal Navy could continue modifying existing carriers, but the margins were narrowing. Britain's political ambitions were also changing. The country was reconsidering the cost of maintaining large forces overseas. Aircraft carriers required not only ships and aircraft, but trained aircrew, escorts, supply vessels, dockyard capacity, and thousands of sailors. In the 1966 Defense Review, the British government announced that it would retain the existing carrier force into the 1970s, but would not order a new generation of conventional fleet carriers. The proposed CVA-01 carrier was cancelled. The decision placed every existing carrier inside a closing timetable. However capable the ships remained, there would be no direct replacement for them. HMS Victorious was scheduled to leave service in 1969. By 1967, she had served for nearly a decade since reconstruction. The enormous investment had not produced the several decades of service expected from a new hull, but neither had it produced a useless ship. She had operated around the world, participated in major exercises, supported deterrence operations, and demonstrated some of the most advanced naval aviation systems of her period. Her tragedy was not that the reconstruction had failed. It was that the reconstruction had taken so long and cost so much that by the time the ship returned, changes in aircraft technology and national strategy had already begun shortening the future for which she had been rebuilt. In November 1967, Victorious was nearing the end of another refit at Portsmouth. Then the fire broke out. One sailor died, 2 were hospitalized. The damage was surveyed, and repair work began. But the government now faced a narrow calculation. The carrier was due to leave service in 1969. Completing the refit and repairing the fire damage would cost approximately £300,000. Keeping the ship in reserve would also require substantial expenditure, while returning her to service would preserve her for only a limited period under the existing defense plan. Scrapping her immediately was expected to save millions of pounds in the following year. The fire did not provide proof that the ship was structurally finished. It provided the final event that turned an approaching retirement into an immediate one. The government ordered HMS Victorious to be paid off and disposed of. She was de-equipped and sold for scrap in 1969. In July 1970, she arrived at Faslane to be broken apart. The carrier that had survived Bismarck Arctic waters, Pacific combat, kamikaze attacks, and 8 years of reconstruction was finally defeated by a combination of fire, remaining service life, and national policy. It is tempting to reduce HMS Victorious to a simple lesson. One version presents her as an engineering miracle destroyed by short-sighted politicians. Another presents her as proof that rebuilding old warships is always a false economy. Neither explanation is sufficient. The reconstruction was undeniably expensive and slow. Requirements expanded after work had begun. A modernization initially estimated in the millions eventually cost nearly £20 million. The project occupied Portsmouth Dockyard for almost 8 years while the technologies it incorporated were already spreading through other fleets. A purpose-built carrier could have been designed around jet aircraft from the keel upward. Victorious had to accept every improvement through the constraints of an armored hull conceived in 1937. But the result was not a failure. She returned to service with new boilers, powerful catapults, an angled deck, optical landing aids, advanced radar, and a comprehensive fighter direction system. She remained operational for almost 10 years after reconstruction and demonstrated genuine military value. The more accurate lesson is about uncontrolled scope and diminishing returns. Modernizing an old platform can be worthwhile when the requirements are clearly defined and the remaining service life justifies the investment. It becomes dangerous when the project must chase rapidly changing technology, when each improvement creates new structural demands, and when national strategy changes before the work is complete. HMS Victorious was caught in all three conditions. Her designers were trying to solve the problems of the jet age. Her dockyard was trying to fit those solutions inside an armored wartime structure. Her government was trying to preserve global power while reducing the cost of maintaining it. The ship became the physical meeting point of those incompatible pressures. The steel of HMS Victorious disappeared at Fast Lane. The ideas embodied in her did not. The angled flight deck became essential to carriers that launch and recover conventional fixed-wing aircraft. The mirror landing site evolved into modern optical landing systems. The steam catapult served for generations and remains in use on several carrier classes, while the newest American carriers have moved to electromagnetic launch systems. Landing signal officers remain part of carrier aviation, now working with technology that gives pilots far more precise guidance than the batsmen of the early post-war years possessed. No single ship invented this entire system, but HMS Victorious represented the moment when many of its essential components were brought together in a carrier rebuilt for operational service. She was not the prototype for every carrier that followed. She was something more historically revealing, a full-scale experiment in whether a navy could force the future into the body of the past. The experiment succeeded technically. It proved much more difficult economically. And before Britain could fully exploit what it had created, the country decided that it could no longer afford the kind of global naval force for which the ship had been rebuilt. HMS Victorious was built to fight one war, reconstructed for another, and retired because Britain's idea of its own future had changed. Her hull vanished, her solutions became standard. And every time a conventional carrier aircraft follows an optical glide path toward an angled deck, misses the wires, applies power, and climbs safely away, it repeats a maneuver made possible by the aviation revolution that HMS Victorious helped carry to sea.